The first lecture looked at NMR theory, which was 16.1 to 16.2 of your text. Now we're going to look at 16.3, which are characteristics of NMR, of a proton NMR spectrum. Prior to doing 16.4, I'm going to talk about 16.5, which is the chemical shift. Then we'll come back to 16.4 and we'll go through 16.6, which is integration. Okay, 16.4 is actually chemical equivalence. And then we'll move on to 16.7, which deals with multiplicity. So here we have an NMR spectrum. Specifically, this is a proton NMR spectrum. So what type of information can we get from the spectrum? We can use the location of each signal. This will tell us about the electronic environment of each proton. 2, we can look at the area under each signal. This will allow us to determine how many protons correspond to each signal. And finally, we can look at the shape of the signal. And this will give us information about neighboring hydrogens. Okay, so let's address point number 1. Here you can see it says the chemical shift, and it's in ppm, so that's parts per million. And we'll talk about that in later slides when we specifically address chemical shift. So you can see typically the scale goes from 0, and usually proton goes up to 12 ppm, although it's not shown here. Now you can see, so signals that are located closer to 0 have a different chemical environment than signals that are located around 7 ppm. So the location is going to give us information about the electronic environment. We can take a signal and we can integrate the area underneath the peak, and this will tell us how many protons correspond to that specific signal. Next, if you look at the shapes of the signals, they're different. Now the shape will tell us about neighboring hydrogens. In addition, we need to look at the number of signals. Okay, and this will be addressed in 16.4 because this looks at chemical equivalence. If you remember from carbon NMR, the number of signals tells you how many the number of unique hydrogens that we have, of chemically unique hydrogens. So let's talk about chemical shift. This is section 16.5. So why do hydrogens have signals at different ppms along the spectrum? Now this has to do with the fact that each hydrogen has an electron associated with it. And as we discussed before, electrons are negative. Electrons are negative charges that move. When they move, they generate a magnetic field. So if we go back, and if you remember, we have our hydrogens that are randomly aligned. We apply a field, a magnetic field, B0 of some strength. Some spins will align with the field in the alpha spin state, and some will oppose it. We're going to apply an RF pulse, which is a range of radio frequency. And when we hit the right energy, the right delta E, we will flip the spins to the beta state and leave the alpha state unpopulated. Then we have relaxation back to alpha, and a signal is recorded. What happens is that the electrons will generate a magnetic field that opposes the applied field. As a result, this will shield the hydrogen from the applied field, so that it feels less of the applied field of B0. So if we think back to that spectrum, I can pull it up again. We can see here, okay, this region is considered upfield, and this is downfield. Now upfield has increased shielding, where the nuclei feel less of the applied field. Downfield we have de-shielding, where the nuclei feel more of the applied field B0. It will help to look at this in terms of specific chemical structures. So for example, here is a structure of methane. And here I have chloromethane. Now, the hydrogens, okay, let's ignore equivalence at this point. If we look at this hydrogen and this carbon, there is little difference in electronegativity. The electron of hydrogen stays with the hydrogen, and as a result, the hydrogen is shielded from the applied field B0. So the signal will be upfield. Chlorine is more electronegative than carbon. So the electron density is pulled towards the chlorine. As a result, the hydrogen, that electron, is not as close to the hydrogen nucleus. As a result, shielding is reduced and the signal will shift downfield. So if we were to ignore splitting at this point, this signal would be more similar to a signal that you would get from a hydrogen that is not near an electronegative group. Okay, not near Cl. And this signal would correspond to something electronegative near the hydrogen. This effect is called the inductive effect. And you should be familiar with this from last semester. So if you need to recall it, go back to section 1.11, where the inductive effect and electronegative atoms were talked about. And so what we can see, and I'll just draw the series for you that's in your book. We're going to be looking at the chemical shift of the yellow hydrogen. Again, I'm ignoring equivalence at this point. And so when we look at the chemical shift without a halogen is 1 ppm. When we have an iodine present, it's 2.2 ppm, 2.7 with a bromine, 3.1 with a chlorine, and all the way to 4.3 with a fluorine. The more halogens we add, the more significant the effect. Thing that we need to look over is that the inductive effect decreases as you move away the distance increases. From the electronegative atom. So for example, if we look at 1-chloropropane, we can see that here the chemical shift would be 3.3 ppm. Here it would be 1.6 ppm for these hydrogens, and finally 0.9 ppm. The further you are away from the chlorine, the less of the strength of the inductive effect. So I stated in the previous lecture that I would like you to be able to draw an NMR spectrum based upon a given chemical structure. So if we commit a few numbers to memory, it is possible to predict the chemical shifts for protons in a variety of compounds. So these are coming from your book. So for methyl hydrogens, 0.9 ppm. For methylene, it's 1.2 ppm. And for methine, it's 1.7 ppm. Now, an oxygen of an alcohol or an ether will shift a signal 2.5 ppm downfield. Oxygens of an ester will have an effect of 3 ppm downfield, and a carbonyl will have an effect of 1 ppm downfield. And so if we look at a couple of structures, I'll show you how we can predict the values. Again, this is coming from your book. This is table 16.1. So for example, here we have ethanol, now here's your alcohol. This is the alpha carbon, this is the beta carbon. The alpha carbon is bonded to the functional group. You should remember this from last semester. If you were to look at the chemical shift of these hydrogens, it's a methylene group, which is a CH2, which we said would typically be around 1.2 ppm. It's directly next to the oxygen of an alcohol, so we are going to add 2.5 ppm. So the chemical shift should be around 3.7 ppm. And so you can use these estimates to estimate chemical shifts. When we look at the movement of pi electrons, such as the pi electrons in a benzene ring, we see another unique phenomenon occur. So here you have the movement of pi electrons. And the movement of the pi electrons will cause a magnetic field to occur. Now, the direction of that magnetic field, if you look at this figure from your textbook, is that the electrons, let me switch colors, are moving like this around the ring. Now, here's the applied magnetic field. So you have this circulating current, the dark blue, you have the plane. So you have circulating electrons, that will induce a magnetic field that is perpendicular to the plane. Now, this field moves in through the ring and then out. Here's the applied field. So inside the ring, any nuclei that you have will be shielded. Similar to the effects we looked at previously of just isolated electrons in an alkane. Outside the field, where you typically have your aromatic hydrogens, so outside the ring, you can see the induced field adds to or follows the same direction as B0, which is your applied field, so that any hydrogens outside the ring are de-shielded. And that is why aromatic hydrogens can be found between 6 to 8 ppm. Now, before we wrap up our discussion about chemical shift, I'd like to discuss why the chemical shift is expressed in ppm. So the chemical shift is expressed in ppm. It gives you the location of a signal. It can be expressed using the Greek letter delta. It is in relation to a reference compound, and that reference compound is TMS, or tetramethylsilane. So that's TMS. So now, when you're recording an NMR, you have the frequency in hertz and this is, you're using frequency because you're using a radio frequency to excite the spins. So you're looking at the frequency in hertz, you're looking at the difference between the resonance frequency, that's the frequency that corresponds to delta E to promote alpha to beta, and that of TMS. So delta is going to equal the observed shift from TMS in hertz times 10 to the 6th divided by the operating frequency of the instrument. When we express a chemical shift in terms of this unit delta, or in parts per million, this way we're able to have the same chemical shift regardless of the instrument strength. The chemical shift is constant if we have an instrument that is 300 megahertz or an instrument that is 60 megahertz. We will still have the same chemical shift. Please familiarize yourselves with table 16.2. This gives chemical shifts for protons. You will be given this information on an exam, but it would help you to become familiar with it. So this concludes the discussion of chemical shift. In the next video, I'm going to discuss chemical equivalence.